very good morning to you all. A couple of classes back, so we were discussing about one of the ground improvement techniques. So that is the sand drain or the PVD. While on the whiteboard, I could able to explain a lot of fundamentals, but a couple of the things that were missed at that time. So I thought I will show some kind of the schematics of how the PVD is installed in the field, how the PVD looks like. So all those details I thought I would share in the form of a PVD. So let me recall a few more fundamentals about the PVD technology. So as I told, PVD designates for the prefabricated vertical drain. So in short, it is called as a PVD. So this is a typical schematic of a PVD. If you look at closely, this has basically two components. The inside is called as a core, which is made of a polypropylene material, while the outside, which is wrapped up with some fabric called as a geotextile. While if you look at the schematic of a PVD, so this is not a circular geometry, which is typically possible in case of the sand drain. While this is a rectangular cross section, normally it is called as oblong. The typical length of any PVD lies between 95 to 100 millimeter, while its width is 3 to 5 millimeter thick. It is a very slender material. The width is very small. The thickness is very small, while width is reasonably large. So it is totally made of a synthetic material. While inside core is a very hard material, while outside geotextile is a very soft material. These are the functions of the PVD. The core will primarily act as a free drainage channel, where it allows the movement of water in the upward direction as a result of the generation of the excess pore water pressure. While the non-woven filter jacket, as shown here, so this is the filter jacket which is wrapped around the core material. So it acts as some kind of the retention mechanism. It allows only the water to drain inside the core while retaining the soil particles. It's some kind of the filtration mechanism. That's why it is called as a filter jacket. The function is to prevent the soil surrounding the drain from entering the central core, but allows water to flow. Now, when I said, so it acts as some kind of the filtering media, then one important point that should come to anybody's mind is the filter should be a porous material. That is the first thing. Second thing is it is a boundary between a hard plastic core and the soil. So because of the gradient or because of the mixing of the soil with the water, so this soil always tries to carry or migrate the finer soil particles. So these finer soil particles, if they enter into the core, then they will drastically hamper the permeability character or the capillary property of the core. So therefore, this filter mechanism or this filter jacket so retains the migration of the soil particles and thereby allows only water. So this is also fundamental, the very fundamental that we have already discussed it. So on the left side picture, it shows a typical one-dimensional consolidation where it takes predominantly longer times in the form of years, while on the right side, so we have accelerated the consolidation phenomenon by shortening the path traveled by the water molecules. So for shortening the path, we have installed something called as a PVD at a specified intervals. So in fact, that spacing between two PVDs is one of the design parameters, as you can see in this schematic. This is the real life pictures. Suppose if you go to the field and if you see how the PVDs are installed, then so this is how the photographs look like. So the upper and lower. So if you scrutiny these two pictures, up and lower pictures, you can notice that first of all, there is small amount of the PVD is protruded above the ground. So maybe a feet or less than a feet or approximately a feet of this each PVD is so lied above the ground surface. So this is basically meant for two purposes. If you recall, so right on top of the natural ground, we always has to provide some kind of the blanket layer. So therefore, this protruded PVD will be directly inserted in that blanket layer. So in the above picture you can see. So this is some kind of the sand, and you can also see so the upward movement or the water squeezing out from the ground or some kind of the dampness. But of course this is right at the installation time, but with the time you can notice the movement of the water coming from the down to the upward direction. And the moment you provide the drainage blanket, it makes an interconnection of all the water or all the PVDs. So as we can see in the right side bottom diagram. So this is how, so the water which is seeping in the upward direction from the bottom will be collected in the blanket, and from there it is diverted to a some or some collection tank. And the above right side above picture that shows how the PVD is installed in the ground. So this is a simple device. We can have in the next slide the more accurate details of how it is exactly inserted in the ground. So this slide will show you how exactly it is installed in the ground. So first of all, this is a, here you can see there is an original ground. So into which we are inserting the PVD. But PVD is some kind of the strip. So it has to be attached to some device that is called as a mandrel. So this mandrel is attached to the machine. So here the mandrel and the PVD are attached. But we need to have some mechanism where the bottom, at the bottom of the mandrel, so the PVD has to be anchored properly, which otherwise only mandrel will be advanced into the bore pore, but the PVD will be retained on the ground surface. So therefore, there should be a firm fixation between PVD and the mandrel. So in a sense, the mandrel has to carry the PVD. So what they do is they provide some kind of the anchoring mechanism at the bottom. So here you can see. So for that purpose, an anchor plate is used. So this anchor plate is permanently retained inside the ground. So when the mandrel is driven into the ground, so the PVD along with the anchor plate will be inserted, while the anchor plate will be left at the bottom only. But there is some mechanism that you can refer to in the form of a passive effect. Suppose if you look at the bottom diagram, so here, so you can see since the soil is very soft, the moment you stop advancement of the mandrel into the soft soil, so the soil surrounding the anchor plate will flow into the anchor plates and thereby provide some kind of the passive resistance. And thereby, when you retract the mandrel, so because of this passive resistance from the soil, you will retract only the mandrel, but you will retain the PVD along with the anchor plate at that location. So this is a very simple mechanism. So for driving the PVD. So in the there are some fundamental reasons why should we go for the PVD technology over the sand drain. So first of all, installation of the PVDs is quick, and almost 6,000 linear meters of the PVDs can be installed in a day, while that is practically impossible in case of the sand drain. So no risk of PVDs breaking because these are the monolithic plastic material, while in case of the sand drain, since these are the particulate material, there is a possibility of the breakage or discontinuities of the sand drain. So no risk of the shear failure, no risk of the breaking, and no risk of the shear failure in case of the PVD. So these are the greatest advantages. Then the discharge capacities of the PVD is significantly higher than the sand drain. So for here they have given a typical comparison of the 350 millimeter diameter sand drain with the typically or normally used PVD. So that is, here you can see the discharge capacities of PVD are in the range of 30 to 90 into 10 power minus 6 cubic meter per second, while that of the 350 millimeter diameter sand drain is 20 into 10 power minus 6 cubic meter per second. So the discharge capacity of the PVD is higher than the sand drain. This is another advantage. So when installed with the purpose designed mandrel, smear effect. Smear effect means when the mandrel is advanced into the borehole, so it makes some kind of the disturbance on the walls of the borehole. That is called as the smear effect. Smear effect, you can also see when you apply any soil on the wall, that is called as the smear effect. The obvious consequence of any smear effect is it blocks the force. Now you can see, if I make a borehole, unless I have a proper interconnection in the form of a force between the hole and the native soil, the water will not easily squeeze or permeate into the borehole. So what happens is, if the borehole walls got smeared, so that means very less number of pores are available or connecting between the pores and the soil. So therefore, less is the smear effect, more is the permeability of water entering the borehole. So, but we cannot totally avoid the smear effect. So there is some extent of the smear effect is possible during the installation of the PVD. So therefore, this has to be accounted for when you design any PVD or the sampling. So PVDs are consistent as they are factory produced. So we have some kind of the control over the PVD manufacturing, while that is practically not possible in case of the samples. So this is some information about the discharge capacity. The typical discharge capacity of the PVD is 158 cubic meter per year, so which is exhaustively very high, and with an hydraulic gradient of approximately 0.1. So this is a very low hydraulic gradient. And there are few factors which can impact the discharge capacity of the PVD, which include deformation and creep of the filter into the pore, permeability reduction due to clogging of filter and pore, bending and kinking of PVD during the settlement, pressure and flow. So these are the few factors that you need to look into while you design any PVD. So because you notice when you have discussed in the first class, the deformations could be in the order of a meters at the feet. You can imagine when you install the PVD, you install for a certain meter, say for example 10 meter. But after say 3 months or 4th month, it is not a 10 meter. It could be 9.5 meter or 9.2 meter. That means there is a deformation or the kinking or the bending of approximately 750 millimeter. So that deformation will impact the overall the discharge capacity of the PVD. So therefore, these kind of the factors you need to consider and account for in the design of the PVD. So there are some formulas. The discharge capacity is measured as the total discharge by the hydraulic gradient that is maintained. And here the flow is very slow, so therefore the discharge is valid under laminar condition only. And this is how the efficiency of the PVD is measured. So when they do, once the product is out, they will try to measure its discharge capacity by relating the total discharge cubic meter per second versus by maintaining the different hydraulic gradients. So from this graph you can see that as long as hydraulic gradient of 0.1 only, the PVDs perform very well. Behind that, their performance drastically decreases. So therefore, when you use the PVD, ensure that the hydraulic gradient has not exceeded the 0.1. And we were also discussing about equivalent diameter of the PVD. So I also told there are several variety of the formulas available. So depending upon the origin of the country, depending upon the overall performance, several people has proposed different equations. So you can go through any book or you can use any of these equations. You are most welcome. So then there are other things like equivalent diameter of the PVD based on perimeter equivalence. So this we did not discuss. So this is the equation that you can use based on the perimeter equivalence to determine the equivalent diameter of the frame. Then before we install the PVD in the ground, so we need to assess or we need to ascertain so whether the discharge with which it is able to dewater the ground is meeting or not. So for that verification purpose, so you can use this formula. So the total discharge capacity should be greater than or equal to 7.85 into factor of safety into Kr into H square. So where QC is required discharge capacity of a PVD FS is factor of safety, typically 4 to 6. KR is radial permeability of the soil. HDR is maximum drainage distance of the PVD. So once it is ascertained that the total QC is greater than this formula, then only that PVD is allowed to use in the ground. Otherwise, that product will be strictly discarded. So the another important factor that we have discussed is we are dealing with the two medium. One is the geotextile. So each geotextile is made for a particular aperture size or apertures. While on the other hand, there is a solid soil material. So it is obvious that when soil particles tries to enter into the geotextile, they won't easily allow, and but at the same time they will not move back. So thereby they will clog the apertures of the geotextile. So the obvious consequence of the clogging is minimization of the drainage or the discharge capacity. So therefore, to ensure the maximum drainage within the stipulated period of that particular product or that particular project, so we need to verify its drainage capacity using these formulas. For example, O is aperture size. So O95, apparent opening size of geotextile filter, should be less than or equal to 2 to 3 times of D85. That is soil particle size of 85% of the fiber. As you know, it is similar like your D10, D30, D60. Here it is a D85. Similarly, O50 should be less than or equal to 10 to 12 times of D50. So these are some criterion to understand the drainage properties of the geotextile method, but concurrently we are also avoiding the possible clogging of the geotextile within the stipulated period of that process. Then the drainage criteria for the geotextile, so Kc should be greater than 10 times of the Kr, where Kc is the permeability of the PVD. So it is also certain if the permeability of the PVD is lesser than the soil. Now we can understand what will happen. So therefore, the permeability of the filter shall be at least 10 times higher than the permeability of the soil. Now to understand or to assess the clogging resistance requirements of the geotextile filter, we can use this formula. Like for example, the porosity of the filter should be greater than or equal to 30%. O95, that is apparent opening size of the geotextile, shall be greater than or equal to 3 times the D50. Then other formula, O15 shall be greater than or equal to 2 to 3 times of the D10. So these are some criterion set by the different people in order to make sure that during the project, during the lifespan of the project, so the PVD works very well or with highest performance possible. There is another concept that is called as the equivalent permeability. Now you know we are installing the number of PVDs into the ground. But there was another concept that was evolved is, what if I consider or if I assume all the PVDs are working at the same degree, at the same rate, and thereby I can assume that the volume as a single block. That is called as the equivalent permeability. Here you can see. So in reality, there is the horizontal permeability, there is a vertical permeability, so of the soil. But if I take the equivalent permeability, it is the combination of the horizontal and vertical, because I am considering this entire thing as a single monolithic block. It is no more an individual blocks. That means, in a sense, if I take one PVD, it forms some kind of the zone of influence. Now, in a similar sense, if you take KVV, that indicates that this is the zone of influence of all the PVDs together. So that's how we can able to understand the equivalent permeability. So that equivalent permeability will be determined using this formula. So you don't need to remember all these equations, but this is one concept which was proposed by the Chai et al. But for few of the projects, this kind of the concept is really useful. So then, what kind of equations are used? Because we are always talking about how to determine the equivalent diameter, so on and so forth. But how should I calculate what was my degree of consolidation that was achieved over a period of time. So here we can use this equation. UF is equals to 1 minus exponential minus 8dr by alpha dash. So where UP is average degree of consolidation due to radial drainage. It's not UP, it's UR. And this equation you can use where TR is the time factor, alpha is the sum factor. So where TR is equals to CVR into T by dW square, where CVR is coefficient of consolidation due to the radial drainage, and T is the time required, and dW is the equivalent diameter. Here you can show dW is nothing but 2 into A plus B by pi. And the equation for alpha dash is given here, that is n square into m, where m is nothing but n power 4 by the total n power 4 by n square minus s square ln n by this big equation. This equation is meant for to address several issues that may be encountered after installation of the PVD. For example, we did talk about the smear effect, we did talk about the well resistance. So this equation basically accounts for both smear effect as well as well resistance. So here, if you have the parameters are not defined, for example,
Sir,
yeah,
sir, what is the S here?
I'm saying, I'm coming to that point. Okay, here one parameter is n. So n is defined as the ratio of dE by dW. dE means the diameter of the zone of influence. dW is the equivalent diameter or diameter of the sample. While S is this is related to the smear effect. S is related to the smear effect. I will show you that equation, and N is the ratio of dE by dW, and KH is the permeability in the horizontal direction. KV is permeability in the vertical direction. Okay, so here S accounts for the smear effect, KH and KS accounts for the well resistance. Suppose if you use this equation, this accounts for all possible limitations of the PVD. Okay, so this is the equation, and you also do not need to remember most of the equations also. You can also pick up the values of directly UR instead of the calculating using this equation. UR is equal to 1 minus exponential minus 8 dr by alpha dash. Rather, alternatively, you can use this table. Suppose if I know the TR value, I can directly pick up the value of the UR. Or in some cases, you will be provided with this kind of a graph. So here you can see this graph is a function of the several parameters, that is n, which is the ratio of dE by dW, then S that accounts for the smear effect, KH by KS, that is permeability in the horizontal direction to the permeability in the vertical direction, and alpha dash. Okay, so in the exam these graphs will be provided, you don't need to bother. So then another important design parameter is the drain spacing. So drain spacing is related with the drain diameter depending upon the pattern. So generally, two varieties of the patterns are commonly used, that is a triangular pattern and a square pattern. In case of the triangular pattern, the diameter is related with the S by 1.05, while in case of the square pattern, the diameter is related to the spacing by a factor of 1.128. So where D is the diameter of the equivalent cylindrical column of soil, S is spacing between the two PVDs. This is the schematic which is showing, this is typically a square pattern. So this this completely filled rectangle indicates the PVD, where the width of the PVD is small a, thickness of the PVD is small b, and using the A and B it will be converted into equivalent diameter, that is dW, and the outside two circles indicate the zone of one is diameter of S designated the smear zone. S designated, here the another new concept that came into the mind is the smear zone effect. So this white outer circle indicates the native soil. In a sense, this soil is not at all got disturbed because of the driving action. While smear zone means it is the zone which is little bit got disturbed because of the mandrel or the borehole advancement in the soil. Now, what would be the basic distinction between the native soil and the smear zone is the permeability of the smear zone is slightly lesser than the permeability of the native soil. Lesser than the native soil, because when there is a smear effect, this smear effect clogs or blocks some amount of the pores. Thereby, the permeability will get reduced. Okay. So the parameter which I showed in the previous slide, that is S, is a function of the permeability of the soil in the smear zone. The permeability of the soil in the smear zone, which is lesser than the permeability of the original soil or native soil. So this is another formula where, for example, if I know the degree of consolidation that should be achieved, then how much time is required to achieve that particular consolidation. So for example, UT, time required for achieving the certain consolidation, that is UH, average degree of horizontal consolidation. Suppose if I fix horizontal consolidation as 85%, then I can able to calculate for the designed diameter and the spacing what would be the approximate time required. So this formula was proposed by Kaiselman. So therefore it is called as a Kaiselman formula. And these are the steps you can follow to design the PVD. Different people have proposed different theories to determine the overall degree of the consolidation. The very first theory was proposed by the Barons. It is called as a Barons theory. So he has in the year 1944. The basic distinction between different theories are, a few theories have considered like the smear effect, a few theories have considered like a well resistance effect, a few theories have considered they work only in the homogeneous soil, non-homogeneous soil, layered soil, so on and so forth. Or somebody has attempted different parameters. Like somebody has considered only the Darcy's flow, others have considered the non-Darcian flow. So all these are assumptions. So these are the equations proposed by the Baron, where first of all dW is calculated as 2 into A plus B by pi. A is the width of the PVD, B is the thickness of the PVD. So here you can see this is the PVD and this is dW, diameter, equivalent diameter of the PVD, and D is the zone of influence of the PVD. So the average horizontal degree of consolidation can be calculated using the formula of 1 minus e power minus a pH by f of n. So alpha dash and f of n both are same. But there is a small distinction. Now in the alpha dash, if you look at the alpha dash, this is a very big equation. And if you look at carefully, this is n power 4 by n square minus s square into ln n minus n by s minus 3n square minus s square by 4 plus kh by ks. So this last term accounts for the well resistance, while first two terms account for the smear effect. So they accordingly, if you look at this equation, here you can see the f of n is includes only first two terms. It doesn't have the third term. So therefore, I can say here that the f of n accounts for only the smear effect. It doesn't account for the well resistance. Suppose if we include the third term also, then we can say that accounts for both smear effect as well as the well resistance. While for ideal condition, you can directly use the simplified equation, that is ln n minus 0.75. So almost both will give you the same value of the f of n. And th, that is ch into t by d square, and n is the ratio of dE by dW. And alternatively, you will be also provided in the exam this kind of a graph where you can directly pick up the average degree of consolidation in the horizontal and the vertical direction for the known values of the time factor in the vertical and horizontal direction. There is a single trend line for the vertical. However, there are several trend lines for the horizontal degree of consolidation, because for vertical there is only one path, either upward or downward. But when you talk about the radial drainage, so we have different diameters of the drains or different equivalent diameters. So as you change the diameter of the drain, so correspondingly the parameter n also changes. For example, here you can see n is defined as dE by dW. So as you change dW, so there is a change in the equivalent diameter also. So therefore, your n value changes as per the diameter of the sand drain at the PV. So therefore, so for a different values of the n, so different trend lines are the proposed with the PV. Okay, so this graph will be provided in the exam.
Sir,
Yeah.
sir, this theory is for smear effect, no, sir? Why it is written equal strain consolidation with no smear?
Equal strain means the uniform consolidation, uniform settlement.
Sir, actually, I'm asking this theory is based on taking the smear effect, sir. But it is written for no smear, sir.
See, it is very simple. If you look at these equations, suppose if you take fn is f of n is equal to ln n minus 0.75, it doesn't account for the smear effect. Because if you look at this equation, it is n square by n square minus 1. N means it is dE by dW. It is not accounting for the permeability in the smear zone. So therefore, this equation doesn't account for the smear at all.
Sir, what is the equation for the smear term in the previous?
I will show you.
What is the value of S, or what is the equation for S?
S is ratio of ds by dE, or ds by d, either dW or dE, which is the diameter of the smear zone by diameter of either PVD or the equivalent diameter of the PVD. So now
Okay, okay.
it comes somewhere. Uh, okay, so these are different, basically derivation of the equations. You can go through it. One of the important equation is, you need to remember this equation, how to calculate the average degree of the consolidation due to the combined effect of the vertical and horizontal consolidation. So that is 1 minus UVH is equals to 1 minus UV multiplied by 1 minus H. So this equation you need to remember, where UH is 1 minus exponential minus APH by F of n. So F of n without accounting for the smear effect, with only accounting for the smear effect, with smear plus well resistance. Okay, for UE, you have seen already the equations, so I don't need to repeat it again. Now, this slide will also cover everything, UH and UE. So there should not be any question to anyone how to calculate the average degree of consolidation as a result of the combined vertical and radial consolidation. So anybody has any question? Anybody has any question? So this is another chart, solution to combined drainage, combined average degree of consolidation for different lambda values as a function of the time factor, that is TB. So this also will be provided. In fact, we can also develop this kind of the charts because you know the equation, keep on assuming certain values of the CH, CV, D and H. That's it. So this schematic will explain you or will give you more details about the smear effect. So here at the middle where it is shown dW, so this dW designates the diameter of the PVD, diameter of the PVD. Now because of the borehole making, as I told, there is some kind of the disturbance to the borehole walls. That disturbed zone is designated as the smear zone. So ds is the diameter of the smear zone, and the outside dE is the zone of influence of the PVD. And here you can see smear zone means disturbed clay, and the right outside the smear zone is undisturbed. So in the undisturbed clay, so the permeability of it is designated as KH and Kv, while the permeability of the smear zone is designated as Ks, while the permeability of the drain is Kc. So try to distinguish each parameter because there are three media here, so therefore there should be three variety of the permeabilities. Yeah, here, so this equation, as I told, the f of n, how to include the smear effect. So the same equation has been extended to include the smear effect. Now here, the additional parameter comes is S. S is defined as ds by dl, ratio of the zone of diameter smear zone by the diameter of the PV. So the inside blue circle designates the diameter of the PVD. The right outside orange designates the diameter of the smear zone, and the red color indicates the zone of influence of the PV. So now it should be clear to everyone. So what is the PVD, what is the smear zone, and what is the undisturbed or the zone of influence. Then how to account for the smear effect in the consolidation equation. So this is the equation f of n. So this is the equation for f of n. So if you remove the last equation, that becomes no smear effect, no well resistance. And in fact, this is same, repeat, same thing. Uh, so this is some more information. Though I said there is some kind of the smear effect, but it is practically impossible to determine what would be the exact zone of the smear effect. How shall I determine the diameter of the zone? So there are no stipulated guidelines. And in the field also, it is little bit difficult to determine how much zone has got disturbed. So therefore, depending upon the field data, different people has proposed different equations. For example, here as for Head and Mosley, the area of the smear zone AS is nothing but 1.6 times of the area of the cross-sectional mandrel. That is area of the PVD, you can say. Exactly. So similarly, suppose if you can't able to determine the horizontal permeability and vertical permeability separately, so to evaluate the effect of the smear on the permeability, you can take the ratio of KH by KS as 2. So it is obvious that the horizontal permeability is greater than the vertical permeability. Similarly, if you can't able to determine the coefficient of consolidation in the horizontal direction, so you can use this equation alternatively. CH is equal to KH by KV into C. So now let us try to discuss about some design considerations when you want to design the PVD in real life situation. So typically there are two patterns are used, square and triangular. D is equal to 1.13 S for square, 1.06 S for the triangular. And there are different methods and that are used for driving the borehole. Installation, these are called installation methods. Driven or vibratory closed end mandrel, hollow stem continuous slide auger, jetted, driven or vibratory closed ended mandrel, anything. So like sand drain and PVD. So there is a different technology of installation in case of the sand drain and in case of the PVD. And possible drain diameters are the typical spacing and maximum length. That is the maximum depth. So these are the some guidelines given by Holz et al. In the year 1991. These guidelines are to follow. Okay. So then, as I told, usually the PVD technology is useful to accelerate the consolidation in the soft soils. So therefore, how much load should be applied should be decided based on the simple calculation of the permeability, so bearing capacity. So therefore, allowable load is calculated by the simple formula. So P is equals to Q ultimate by the factor of safety. So your Q ultimate is nothing but CNC by the factor of safety, where C is undrained position, NC is the bearing capacity factor, which is typically 5.14 for uniform soft soils, and the factor of safety is typically 1.1 to 1.5. So simply measure the undrained shear strength, put it in this equation, then it gives what should be the subcharge load that should be applied instantaneously at the beginning. And there is suppose if the surcharge load is too high, even before we consolidate the ground, so the entire ground might vulnerable fail under slope stability condition. So therefore you need to analyze what would be the stability condition. So you can use any software. So for that purpose, and time for consolidation, and this is one of the most important factor. So when you go to any client, this is the first question he will ask us: in how much less time you would be able to consolidate the entire ground. That means when I say consolidation, it is 90% of the consolidation or even higher than that. So then one important aspect that you need to understand is, when I say the imposition of the load, it is not an instantaneous phenomenon. Suppose if you look at this graph, so you see there is a sloping line and there is a dotted vertical line. So in fact, most of the equations, they will assume that the load is applied instantaneously, but which is not the case in real life situation. In fact, it is a ramping load. Ramping load means we slowly dump the load on the ground. So that's why it is as time the load increases linearly and we achieve the maximum height. So accordingly, so to account for the initial ramp up period, that is the time required to achieve the maximum height, that is called as the ramp up period. So you can differently calculate the degree of consolidation for ramp up period and post ramp up period using these equations. So there are two different equations to calculate the degree of consolidation, because sometimes the ramp up period is in most of the cases it is in terms of the months only. So you can't able to achieve in days. So then we were talking about only one concept, that is the improvement in the consolidation. But what is the obvious consequence of the improvement? The improvement in the undrained shear strength of the soil. So then how shall I determine how much was the improvement in the undrained shear strength? For that purpose, you can use this equation. Here you can see Cu is equals to XF into over consolidation ratio power some cap multiplied by sigma dash. So that means the improvement of the undrained strength is a function of the amount of the subcharge load that you have applied and the soil type. The soil type is decided by the OCR. Is it normally consolidated soil or over consolidated soil or whatever it is. Then the another parameter that decides the soil type is chi f. So Cu is undrained shear strength, chi f, that is 0.22 plus or minus 0.03 for homogeneous sedimentary clays. So which are designated as the soils lying above the A-line classification. While chi f is 0.25 plus or minus 0.05 for silts and organic soils, those are lying below the A-line. And OCR is the over consolidation ratio. The power cap is 0.88 times 1 minus CR by CC. CR means, suppose when you have done the consolidation, the slope between E versus log sigma is CC, that is compression index. But if you remove the load, then there is a rebound. So that rebound slope is called as a recompression index. Where sigma dash Z is effective consolidation stress, that is overburden pressure. So this is the same equation in terms of again it is correlated with the degree of consolidation. Okay, so because for application of the each sigma dash Z, there is certain amount of the degree of consolidation. So therefore, your improvement in strength, that is undrained shear strength, shall also be as a function of the improvement in the degree of consolidation. So as a result of the applied the surcharge load. So therefore, if you look at this equation, this covers everything. So delta Cu is equals to chi f into OCR power cap into the degree of consolidation into applied surcharge load. So there are some other guidelines also. Here you can see. Since soft soils are often approximately normally consolidated, so we can presume that over consolidation ratio is 1. So in that case, so the chi f of 0.25 can be taken directly. So that if that is the case, if you are assuming so OCR is equals to 1, then your delta Cu is nothing but 0.25 into Ut into P. The P is applied uniform pressure. Ut is the degree of consolidation that is achieved for the applied uniform pressure. And the total undrained strength after preloading. The preloading will not be done in a single sequence. It will be done in 1, 2, 3, 4, 5 number of stages or even more. Suppose if I know the initial undrained shear strength, the increased shear strength is nothing but delta Cu as a result of the applied pressure. Okay, so therefore the net undrained shear strength is Cu1 is equals to the initial undrained shear strength plus the increased or the gained undrained shear strength as a result of applied uniform pressure. So this is how the strength gain will be calculated, and settlement also will be calculated. Your settlement at any time St is equals to degree of consolidation multiplied by the final settlement. Settlement at any time St is equals to Ut into Sf. Sf is final settlement. Ut is the degree of consolidation at that time. This is something called as subcharge effect. Here you can see this can be understood in another sense. First, if you look at all these graphs, there are two periods. The period where we are applying the surcharge load, the period where we are removing the surcharge load once we ascertained that the soil has achieved the desired deformation or the desired degree of consolidation. But thereafter, again, we construct a superstructure on the improved ground. So therefore, we can say PF means the load applied as a result of the permanent load to be applied on the ground, where PS is the difference between the maximum surcharge load which was applied and the permanent load. The combination of PS plus PF is the maximum surcharge load. So when these are the loading conditions, what would happen to the vertical stress in the soil? So initially you can see when there was no stress, there is an initial stress of sigma dash Z0. So when you put the surcharge, when you try to keep on increase the surcharge load, the stress also increases. But upon removal of the load, so there is a removal in the stress in the soil. And there is another way of measuring the same thing is in the form of an excess pore water pressure. When there is a maximum surcharge imposition, at that condition, there was a maximum development of the excess pore water pressure. The moment you stop imposing the surcharge load, and if you are maintaining the same thing, then because of the surcharge load, the excess pore water pressure keeps decreasing. That means it indicates the dissipation. Now, once you attain the desired degree of consolidation, what you do is you try to release the load by removing the surcharge. But at that time, there is some amount of the rebound that you can see here, different rebounds. So that is called as a rebound effective surcharge rate or effective rebound rate. So that's what you need to this. I will skip it. This is not required. This is also not required. So now this is the most important one. So here, how shall I know that I have achieved the maximum deformation? Means, suppose if you draw a relationship between height versus settlement. So here you can see with time elapsed, if the settlement is becoming constant, that indicates that so the soil achieved the desired degree of consolidation or the maximum deformation. For example, here in this case, the maximum deformation occurred at around 9 months. So thereafter, so the deformation is almost constant. In fact, incident, even after removal of the surcharge load a bit, the deformation is still same value. That is maintained same. That means there is not much of the rebound, which is a positive aspect. Because if the rebound is too much, then that is a little danger. Okay. So there should not be much rebound. So it should be merged with the total deformation when there was a maximum surcharge load. So this is one criterion that is commonly used to assess the surcharge period and the amount of the surcharge load and to terminate the entire project. So these are the another graphs which has been drawn for different things. So the red one indicates the after the removal of the surcharge. So here this is the PVD. This is the PVD. So right on the ground surface there is a negative pore water pressure, and below 7.5 meter there is a positive pore water pressure. So then after up here, this is after the removal of the surcharge. Then the black line after half a year. Then this blue line at the end of the filling. At the end of the filling. So this is on the pore water pressure that they measure. So initial pore water pressure is almost 20 kilopascals without surcharge, and after imposition of the maximum surcharge, it rose to around 85 kilopascals. Around 85 kilopascals. Now you can also clearly distinguish right beneath the PVD and right above the PVD. So right above the PVD, there is a drastic decrease of the excess pore water pressure from as high as 80 kilopascals to as low as 20 kilopascals, or in fact below 20 kilopascals. But you can also see some kind of the influence right beneath the PVD, but not totally, to certain depth. So especially from 20 to 25. So here you can see initial pore water pressure was 80, but it was reduced to approximately 50 kilopascals, but not behind that. Not behind. So here, in a sense, we should understand that we need to have some kind of the monitoring mechanism by which the performance of the PVD is assessed. One monitoring aspect parameter is the deformation. The second one is pore water pressure. So you need to install the device to monitor the deformation. You need to install within the soil to measure the increment or decrement in the pore water pressure. Then only we can able to back calculate what would be the degree of consolidation that we have achieved with time. Because initially when we have designed, we assumed different parameters. But when you have executed the same design in the field, that should be assessed by measuring the parameters, not with the design. That's why it is called as a verification of the design. Verification of the, okay. So this is all about your PVD technology.
Sir,
Yes.
sir, can you explain the red line at a depth of 0 to 5 meters, sir?
0 to
Why
5,
it is
that is something called as a negative pore water pressure and positive pore water pressure. Negative means here the soil doesn't have any water, in fact. It is a dry soil. So below 7.5 meter, positive pore water means there is some amount of the water is there, but that water is also bearing small amount of the load. No water and water.
for water pressure? 0 to
Yeah,
5 meter.
yeah. There is no pore water.
Okay.
Yeah. So anybody has any question?
Sir,
Yeah, Vishal.
sir, there is so much formula, so we have to remember, sir, all this formula.
No, no, no. You basically need to remember only 2 to 3 equations. Uh, only this slide, yeah. Only this much you need to remember. That's it. Nothing more. If you can able to remember this slide, this will cover almost everything.
Okay, sir. And others or parameters formula will be provided.
All parameters means, like for example here, suppose if you are not given the area of the smear zone, then you can say it is approximately 1.6 times of the area of the borehole. Suppose usually we will give all the parameters, but in case if it is not given, then you can use this slide.
Okay, sir.
Okay. So any other question? So I'll stop recording.